You are all that matters. Hello, good morning, good afternoon, and good evening to everyone. Welcome to this online tutorial with short tutorials. Today our focus will be specifically on sets, something more like an intro on sets, and I believe most of us are well acquainted and well familiar with the topic sets. Yeah. Okay. Talking about sets, and I believe it's not the first time we're hearing the word sets. We'll take it up basically from the definition itself. How do we define a set? That's the first thing we can start from. That's where we can start from. How do we define a set? So basically, when you look at a set, from the secondary concept, we know that a set is simply a collection. So a set is just a collection of well defined objects. I'll underline that. Well defined objects. So basically, when it comes to sets, we're supposed to look at the concept of collecting something which is well defined in it. So you cannot just simply call anything to be called a set unless what you're trying to collect inside it is something which is well defined. So basically, in this context, we're simply saying these objects mathematically, we are calling them to be elements. So the objects which are well defined in this case are simply called elements. So for me to have a set, or for me to qualify something to be called a set, I need to collect something which is well defined. So I need to collect something which is well defined. For example, I can collect numbers, I can collect letters, I can collect a number of things specifically as long as they are well defined. So the issue here is defining what you're collecting. Even as you are showing it to a certain individual, someone will be able to identify to say, okay, what you've collected is a set of numbers. So for today, we'll base much emphasis on sets of numbers. So we'll base our much emphasis on sets of numbers. So basically, we've talked about definition of a set. We're trying to simply say that a set is just a collection of well-defined objects. So when we now go into issues of sets of numbers, here we're just trying to collect numbers. So now, if you start counting, you at least will agree with me to say if you were to start counting right now, you will continue counting, and numbers will still be counting themselves until you don't know. You will never reach the end. So basically, these numbers which we can be collecting, they can be in various forms. So specifically, we're talking about when it comes to sets, we have various sets of numbers. For example, we can have a set of natural numbers. We can have a set of whole numbers. We can have a set of integers. So we can have also a set of rational numbers. we can have a set of irrational numbers. We can have a set of real numbers. We can have a set of complex numbers. So basically, when it comes to sets of numbers, the kind of information you're supposed to be able to have in this case should dwell on these categories. So you're supposed to be able to know what kind of a set has natural numbers, what kind of a set has whole numbers, what kind of numbers are integers, rational numbers, irrational numbers, real numbers, or complex numbers. And with the information we are coming with secondary school, I believe most of these we all have an idea of what they are, what natural numbers are, what whole numbers are, what integers are, rational, irrational, real, or complex. Yeah. So basically, we are supposed to be able to define them. Even as you are trying to collect the numbers called natural numbers, there are a lot of numbers in the world, but you're just trying to look for specific numbers. Remember, the set is a collection of well-defined objects. These objects are calling to be elements. So in this case, our elements in this case are numbers. But we're not just going to be picking out any kind of numbers. We're trying to define those numbers which we are picking. What kind of numbers are you collecting? Are you collecting natural numbers? Are you collecting whole numbers? Are you collecting integers? Are you collecting rational numbers? Irrational, real, or complex? Today's lesson, I will simply base my focus on rational and irrational numbers. I know most of the time when it comes to natural numbers, whole numbers, integers, these things, we know what they mean. I believe we've been looking at natural numbers way back from primary, whole numbers way back from primary, all those things. So basically, we are supposed to be able to understand that natural numbers are just simply counting numbers starting from 1. So when you simply say counting numbers starting from 1, we're just talking about numbers like 1, 2, 3, 4, and 2. I don't know. These are natural numbers. But when it comes to whole numbers, we're talking about numbers. These are counting numbers. But in the counting numbers, in this case, we're trying to include 0 to it. So for whole numbers, for a set of whole numbers to qualify, in short, a set of whole numbers consists of natural numbers in it, but we're just adding a certain element which is a 0. So natural numbers plus 0, they make up whole numbers. Yeah. And then for integers, I believe we have ideas. We've been talking about integers way back from grade 4. These are just whole numbers, both positive and negative whole numbers, which also includes 0. Those are integers. Negative numbers, negative 1, 2, negative 2, negative 3, negative 5, including 0, positive 1, positive 4, all negative and positive numbers, including 0, combined together, you will form what are known as integers. Yeah. So our focus for today is on rational numbers. Okay. So we'll talk about rational numbers. That's our emphasis for today. So we'll look at rational numbers. At the same time, we'll also touch the definition of irrational numbers. Once you understand the rational number, automatically you're able to define what an irrational number is. Okay, So what is a rational number by definition? Start from a definition. You understand the definition, automatically things become to be simple for yourself. Okay. What is a rational number? So I'm simply saying that rational numbers are specifically numbers that can be expressed in the form A over B, where A and B are integers, and this B should not be 0. So now look at this. We're simply saying that rational numbers are simply number that can be expressed in the form A over B, where A and B are integers. Where A and B are integers. So basically, if we simply say that where A and B are integers, we have to understand a set of integers, what integers are. And by default, again here, we're trying to put in an emphasis that this B here should not be 0. This B should not be 0. There are some simple mistakes which we always tend to make in mathematics, and which we are supposed to be able to understand, and which we are supposed to be able to, by all means, we never should make that mistake. Every time you are writing a fraction, the denominator should never be 0. That's one thing you're supposed to understand. It is a taboo. It is a taboo to have 0 under the denominator. It is a taboo. If it was maybe in a court case, you're supposed to be detained for I don't know how many years. It is something, a crime. We can never write 0 under the denominator to make your expression undefined, because it makes the expression undefined. So no wonder even every time we're trying to define rational numbers, we're trying to put an emphasis that these are numbers that can be expressed in the form of A over B, where A and B are integers, but this B should not be 0, because if this B is a 0, it makes our expression to be undefined. So that should never be the case. So those are rational numbers which we're trying to talk about. Okay. So now, we are simply talking about these rational numbers. So we have to understand that rational numbers can have we can have more like remarks. We have to understand here. The first remark we can have is that all natural numbers whole numbers and integers are rational numbers. So we're simply saying that all natural numbers, whole numbers, and integers are rational numbers. So we're simply basically trying to, and the basic information you're supposed to understand here is that there's a set of natural numbers, a set of whole numbers, and a set of integers. These sets are subsets of rational numbers. That's the concept you're supposed to be able to understand here. Natural numbers, so in short, we're simply saying a set of natural numbers, whole numbers, and integers are subsets of rational numbers. By subsets, I believe we understand what we mean when we simply call something to be a subset. A set which is formed from another set. Remember, we're still talking about sets of numbers. So basically, in these sets of numbers, it's more like rational numbers, it's more like the mother. That's where natural numbers will come from. That's where whole numbers are coming from. And that's where integers are coming from. So all these numbers are able to be expressed in the form of A over B. For example, 5. 5 can be expressed in the form of A over B. 5 over 1 is a rational number, and so forth. So all those categories. Then the second remark we're supposed to be able to understand here is that all terminating decimals are rational. So all terminating decimals are rational. All terminating decimals are rational. What do we mean? Example which we can give, e.g., we were talking about something like maybe 1.5. This is a decimal number, but keep in mind it is terminating. There are some numbers which are non-terminating. You do not know the end. You do not know the end, whereby it will be continuous 1.4321 until we don't know the end. They can't terminate. But in this case, when it comes to rational numbers, we're simply saying that all terminating decimals are rational. All terminating decimals are rational. 1.5, it is a decimal number, but it is terminating. As you can see, after a point, the only number we have is a 5. It has terminated, it has ended. And then maybe another example we can give as well, maybe 30.1. It is a terminating decimal number. So remember, rational numbers, any number which can be written in the form of A over B. Rational numbers, any number which can be written in the form of A over B. This 1.5, you agree with me that this 1.5 is the same as writing it as 3 over 2. You agree with me that the 1.5 can still be written as 3 over 2, where this guy can more like be our A and this guy can more like be our B. So 1.5 can be written in the form of A over B, where A is 3 and B is 2. Same applies with 30.1. This 30.1 can be written as 301 over 18. You agree with me? So punch 3 over 2 on your calculator to give you 1.5. expand 301 over divided by 10 on your calculator to give you a 30.1. So that is the characteristic which we are simply saying that all terminating decimals are rational. All terminating decimals are rational. Why? Because they are able to be expressed in the form of A over B. Okay. Third remark which we can talk about. The third remark which we can talk about, we're simply talking about non-terminating and repeating decimals are rational. So we're simply talking about non-terminating and repeating decimals are rational. What do we mean? Non-terminating and repeating decimals are rational. Now look at this. Here we had 1.5. This is a terminating decimal, 1.5. After a point, the number is terminated, it is just ending at 5. But there are numbers whereby when you punch on a calculator, they don't end. They are continuously running. But in the continuous running, we are simply saying that they are non-terminating, but numbers after a point, they are repeating decimals. That is the characteristic we're supposed to be able to understand. For example, if I simply say 0.3416713, it continues. So 0.3167132. This is non-terminating. It is not ending. It's not ending. It means that it is a non-terminating number. But there's a concept of repeating decimals. These decimals here are not repeating. They are different. It is non-terminating. After a point, I have 3, 4, 1, 6, 7, 1, 3, 2. The numbers are just continuously running with different values. Hence, it is not repeating. So basically, if I look at this guy is an irrational number. This guy is an irrational number. But if I look at a number whereby I'm talking about 0.333333, if you look at this, what is happening here is that this is a non-terminating decimal number, but it has repeating decimals. It is a non-terminating but has repeating decimals. What are the repeating decimals? I can observe that after a decimal point, there's just a specific value which is repeating itself throughout. This will continuously be moving until I don't know. So it is qualified to be called a non-terminating because this 3 will continue to be moving until I don't know. And the 3 is repeated. The 3 is repeated. So non-terminating and repeating decimals are rational numbers. For example, this 0.3333 is a rational number. Rational numbers, remember by definition, rational numbers are any numbers which can be expressed in the form of A over B. They can be expressed in the form of A over B. So basically, if this can be expressed in the form of A over B, we'll talk about how to express it later on, but I'm just trying to give in remarks and characteristics of these rational numbers. So you basically understand that this 0.33 as a fraction, it is the same as this guy is the same as 1 over 3. So punch 1 over 3 on your calculator, or maybe say 1 divided by 3. The answer will be 0.3333333333 until you don't know. That is why we're simply saying that this is a non-terminating, meaning that it does not have a definite end. But it not having a definite end, it is repeating decimals. The 3's are repeating. It's qualified to be a rational number. But for this one, 0.341, it is a non-terminating, yes, but it doesn't have something which is repeating. It is 341673132. Until you don't, it's not repeating. These are the two differences we're supposed to be able to understand between rational and irrational numbers. Another example I can give, maybe this is just when you look at 0.33. When you look at 0.33, we're just talking about one repeating decimal. But there are some cases whereby you can have two repeating decimals. For example, I have maybe 3.14. I'm putting a bar on top here to indicate something. Even this 0.33 can be written as 0.3 bar on top. What is the meaning of this bar on top? This bar is an indication that the 3 here is a repeating decimal. Others will prefer writing 0.3 dash, or others will prefer writing 0.3 continuous, something like that. But mathematically, we most of the times, we mostly embrace the bar on top to indicate that this 3 is a repeating decimal. But when you look at the other example, 3.142, the bar here is running way back from 1 to 4. It means that the 1 and the 4 here are the ones which are repeating. So basically, in other terms, we're simply saying that this is the same as 3.1414141414 until you don't know. What does it mean? It means that the 14 is a repeating decimal in this case. The 14 is a repeating decimal in this case. So it is not just only one number which can repeat. Some cases, two numbers are able to repeat themselves, two decimals are able to repeat themselves. So this is a 1 repeating decimal number, and this is a 2 repeating decimals. So remember what we're just from explaining ourselves. We're simply saying that under remarks of rational numbers, we're simply saying that all natural numbers, whole numbers are integers, and integers are rationals. By natural numbers, whole numbers, integers, are simply calling them to be subsets of rational numbers. At the same time, we're simply saying terminating decimals. So terminating decimals, numbers which have a terminating decimal, it means it has a specific end. 1.5, it is not continuous running, it is a specific end, a decimal number which has a specific end. Those are terminating decimals. We're simply calling them also to be rationals. And then the third characteristics of rational numbers are simply saying that non-terminating and repeating decimals are rationals. Non-terminating and repeating decimals are rational. 0.333, it is a repeating decimal, the 3 is repeating. 3.141414 is a rational number, the 1414 is repeating. So basically this one, 3.141414, can be written as something like 311 over 99 in terms of a fraction. And you agree with me that this is the form of A over B. So punch 311 divided by 99, you discover that this will be a repeating decimal number, which is 3.141414141414, and so forth. Okay. Now let's look at some of the examples which we can tackle under these rational numbers. Okay. So let's look at some of the examples which we can look at. So this one I can simply say we are going to express the following decimals in the form So we have these three here, and we're being told to express the following decimals in the form of m over n. Remember, we simply said that anything which can be expressed in the form of m over n, where m and n are members of integers and n is not equal to 0, automatically by default those numbers are qualified to be called rational numbers. So we've looked at characteristics of rational numbers. So even as you are looking at decimal numbers, you're supposed to be able to tell, to say, okay, can this decimal number qualify to be called a rational number before I do anything? Ask yourself that question. Do they qualify to be called a rational number? That is the first thing. Excuse me. So if you have 0.3333 and you're being told to express it in the form of m over n, it means that you have to understand, is this a rational number for it to be expressed in this form? Once you understand that it is a rational number, then you can automatically even convince yourself it's okay, indeed it can be expressed in that format. So what do we do now? Let's look at the first one. So we have 0.3333, and then we are being told to say express it in the form of m over n. What do we do? So basically this is a simple thing. So how I'm going to handle it, first I'm going to simply say let. So now when you are letting, we are going to let this number be maybe any letter of our choice. We know most of the times x is the common letter which we tend to use, but we can simply say let x be 0.3333, something of such. So if x is 0.33, this is the same as, we know if it is 0.33, it is the same as 0.3 and a bar on top. I believe I've explained what a bar means most of the times. So if I write a bar on top of 3, it means that 3 is a repeating decimal, which qualifies this number to be called a rational number. First step. Okay, so now we have 0.33. So now what I'm going to do, that this is my x, this is my x. So I'm going to do is, we're going to simply say multiply x by 10. So we're going to, in short, maybe we can simply, in simple terms, or maybe something we can understand, we can simply say multiply throughout this expression by 10. Or let me write it and say multiply throughout by 10. So now, if I multiply throughout this expression by 10, what am I going to have? If I multiply throughout this expression by 10, what am I going to have? So I'm going to have 10 multiplied by this x. What do I have? I'm going to have a 10x, which is equal to multiplying this 10 by this number. Remember, I believe you know how to multiply decimals by 10 or 100 and the like. So this decimal number or this decimal point will move to the right hand side depending on what value I'm multiplying it with. So if you're multiplying the decimal number by 10, the decimal point will move one to the right hand side. So this decimal point is going to move once to the right hand side. I believe we are able to, or even if it was school of business, most of the times we're at liberty to use calculators. It's okay. 0.333 times 10, punch it on your calculator, it's okay. And boom, you have your answer. So we're simply saying 0.333 multiplied by 10. We're going to have 3.333. Remember, these 3's are repeated. So if this point moves here, boom, I'm going to have 3.333. But to indicate that these 3's are repeated, I'm just going to put a bar on top here. So now, what do I have in this case? What do I have in this case? Now, what I have in this case, I have 10x equal to 3.333. This can be more like my first expression. And remember, you also had another expression which you called to be x to be equal to 0.3 bar. This can be your second expression. Okay, so now basically what are we doing? Our aim here, which is just to make sure that numbers after the point are the same. So our aim, it is to make sure that numbers after the point are the same. So I'm going to have two expressions. Our aim is to have two expressions which should have same numbers after a point. So these numbers after a point must be the same repeating numbers after the point. So now the two expressions I have in this case, the first expression has 3.3 which is repeating and 0.3 which is repeating. These are the two expressions which I need, because after a point I only need same repeated numbers. So I have 3 which is repeating in the first expression and another 3 repeating in the second expression, which qualifies. So from there now, I'm going to subtract the two expressions. So by subtracting the two expressions, what we're trying to say here is that I'm going to say 10x minus my x. So if you say 10x minus x, 10x it is this guy and x is this guy. So 10x minus x is the same as 3.3 which is repeating minus 0.3, which is repeating. So you now go ahead and ask yourself, okay, what is 10x minus x? Even without thinking, I believe 10x minus x, it is just my x had 10 funyapo kamo. You're going to have 9x remaining this side to be equal to, and then your right hand direction, we have 3.3 subtract 0.3. 3.3 subtract 0.3. So when you do a subtraction here, you discover that you're just going to remain with a 3. And then from there, the only issue you're supposed to do now, make x a subject. By making x a subject, you can go ahead and divide both sides by 9. 9, this goes, and my x is now going to be equal to 3 over 9. Express this in its simplest form. Automatically 3 into there is 1, 3 in there it's a 3. This is the form which we are looking for. The form which is in the form m over n, which is the irrational number. Okay, let's look at the second one. We're looking at 3.14. So this is B 3.14, and there's a bar on top of 14. So now remember, we want to express it. We want to express it in the form of m over n. That's our m. We want to express it in the form m over n. First thing is first, just as we did in the previous one, we're going to let our x be equal to 3.14. If my x is equal to 3.14, what do I do? We're going to say multiply throughout by 10. Now we have to be very strategic. If you multiply throughout by 10, what is going to happen here is that this point is going to move once, and if it is going to move once, then after I'm going to have 31.4. But remember, our m, it is to have repeating numbers, same repeating numbers. So if two numbers are repeating, I'm not going to multiply this x by 10, but I'm going to multiply the x by 100. Why? So that these 1 and 4 can be moving as 1. Once I move this point, it's going to move 1, 2. So the whole 1 and 4 will move to the left hand side. So they'll be moving as a pair. So the 1 and the 4, they'll be moving as one guy. So for them to move as 1, the only way I can multiply this number, it is multiplying it by 100. This point should move twice to my right hand side. For 1 over 4, for 1, 4, for this number to have the same, for me to have the same repeating numbers. Remember, I need to have two expressions which have the same repeating decimals. The first expression is x equal to 3.14. So the other expression I have after a point, I need to have 1, 4 again after a point. So now look at this. If I multiply this one by 10, I'm going to have something like 10x is equal to 31.4. Now, when you compare this guy and this guy, do they have the same repeating decimals? No. This one is 4, but this one is 1 4. So our main aim it is for us to have the same repeating decimals. Same repeating decimals in these two expressions. The two expressions should have the same repeating decimals. So no wonder I'm going to multiply throughout by 100. So know how many repeating decimals you have there, so that you know the appropriate number to multiply your x with. Are you going to multiply it by 10, 100, sometimes 1,000 or 10,000, even depending with the number of repeating decimals you have? So multiplying through this guy by 100, it means that 100 multiplied by x, I'm going to have 100x, which will be equal to 100 multiplied by 3.14. It means that my point will move twice. I'm going to have 314 point. Remember, the point is now at this point. What numbers am I remaining with this side? I'm still remaining with a 1 4. Where is the 1 4 coming about again? How is the 1 4 coming about again? This is 1 4 is repeating. Instead of me writing 3.14 and the bar, it can still be written as 3.14 14, such that if this point moves twice, 1 2, it will stand here. I'm going to have 314.14. 1 4 is repeating continuously. So here I have 314.14, which 1 4 still continues to repeat itself. So now I have two expressions. The first expression has a repeating 1 4, which this can be called my first expression. The second expression, it is the expression of x, which would be 3.14, the same repeating numbers. What is our goal? Our goal it is to have the same repeating numbers after the point. That is our goal. Next, what are we doing? We are now going to subtract. So we're going to subtract 100x minus this x is the same as 314.14 subtract 3.14. What are we going to have? 100x minus x, we're going to have a 99x to be equal to 314.14 subtract 3.14. What are we going to have? We're going to have something like 311. So in this case we have 99x equal to 311. Next, make your x a subject. So divided by 99, and my x will now be equal to 311 over 99, which is in the form of m over n, which is our goal, Okay, so the last one, but not the least, we have C, which is expressing 0.29432. The bar is running from 4 to 32. You have to be very careful with this one. look at where the bar is starting from. The bar is not starting from 2, it is starting from at 4. It means that the only repeating numbers here is 4, 3, 2. So after the point we have 2, 9, then 4, 3, 2 continues to repeat themselves. 4, 3, 2 will continue to repeat themselves throughout. 4, 3, 2 will continue to repeat themselves throughout. So now, what do I do? If I say let my x be equal to 0.29432. Now remember, we simply said that after the point, that is where we're supposed to have repeating numbers. But in this case, my x has 2, 9, which is not repeating. So this 2, 9 should not be after the point. So first thing, I'm going to make the expression by multiplying this x by how much? 100, so that the point can be at this point. My main goal, it is only to have the repeating numbers after the point. It is only to have repeating numbers after the point. So what I'm going to do, I'm going to simply say multiplying through by 100. Why am I simply saying multiplying through by 100? I want to eliminate the 29 not to be after the point, because 29 is not repeating. The only thing we are repeating is the 4, 3 and the 2. So if this is the case, I'm going to have 100 by x. I'm going to have 100x, which will be equal to 100 by this number, then point to move twice, 1, 2, meaning that I'm going to have 29.432. Done. Next, I'm going to simply say, okay, if this is the case, this is my 100x equal to that. Now we only subtract two expressions which have the same repeating numbers. I will not subtract 100x and x. Why? Because the 100x has the repeating number, which is 432, but the x has a 29 here, which is trying to contradict with our solvings. So I need to do another multiplication so that I can have this third expression. So we have the first expression, which is the expression for x, the second expression, which is the expression for 100x, but this time around I'm going to have the third expression where I'm going to multiply this one now by 1,000, so that this point can move way up to this point. The only way my point here will move until this end if the 100x is multiplied by a 1,000. So now this one can be my expression 2, because my x here was my expression 1. So multiplying expression 2 by a 1,000, it means that this 1,000 by 100x, I'm going to have 100,000 x to be equal to 29.432 by 1,000. It is making the point move 3 times, 1, 2, 3. So it means that I'm going to have 29.432, which was repeated. It has moved this side, 0.432. Remember, the 432 is repeating. So it means that if this 432 has moved to the other side, there is still a 432 remaining after the point. Okay? So from there now, this is my third expression. What did we say? We are simply saying that we only multiply two expressions which have the same repeating numbers. 432 after a point, 432 after a point. So it means that I'm going to subtract. So I'm going to subtract 100,000 x minus 100 x, because these two are the only ones which have the same repeating numbers. So I'm subtracting these two, I'm going to have 29,432.432, which is repeating, minus 29.432. So 100,000 minus 100x, what are we going to have? You can punch in your calculator or you can use your head. We are going to have 9900x to be equal to, you can still punch in on your calculator, 29,432.432 minus 29. That we are going to have something like 29,403. I think so. Confirm. And then from there, as usual, we have to make x a subject. Divide this by 99900. 99900, where my x will now be equal to 29403 over 99900 as a fraction, where if you find the lowest common denominator, or maybe simplifying to lowest terms, we are going to have something like 1089 over 3700 in its lowest terms as a fraction. So this one is the form of m over n, which we are looking for, which is a rational number. So basically, this is how we tend to express decimal numbers into fractions in the form of m over n, considering them that they are rational numbers. Yeah. Then in just a second, let me just give a definition just to distinguish something. Trying to distinguish irrational numbers. So that is how we go about rational numbers. So I believe we have an understanding of what rational numbers are. Now, what are irrational numbers? So irrational numbers in this case are just the opposite of rational numbers. Remember, irrational number is anything which can be in the form of a over b. But when it comes to irrational numbers, it is the opposite. So definition of an irrational number in this case, we're simply saying that numbers that are non-rational. These are numbers that are non-rational. So by non-rational, we are simply saying that numbers that cannot be expressed in the form a over b, where a and b are members of the integer set. I believe we know how to write an integer set is just a z, and b is not equal to 0. That's a definition of irrational numbers. and we simply talked about characteristics of rational numbers. So those characteristics of rational numbers, it is the opposite for irrational. So we are simply saying that when it comes to irrational numbers, rational numbers are all irrational numbers are all non-terminating. Remember we talked about terminating and repeating. So rational numbers are all non-terminating and non-repeating. They are non-terminating, at the same time they are non-repeating. Those are rational numbers. So the example we're talking about, something to do with pi. We know what pi is, I believe. When you look at 22 over, is it 22 over 7 or 22 over 9? No, I love it. I've forgotten. Yeah, but 3.142, that pi number is continuously non-terminating and non-repeating. It will still continue moving and going until I don't know. We talk about the square root of 2. Punch the square root of 2 and you see the decimal number which you are going to have. It is continuous, it is non-terminating and non-repeating. Square root of 3, square root of 6, all those, and etc. All those are irrational numbers. You find a number whereby you write it is 0.314120, 0.42. It is continuously. These numbers are non-repeating, at the same time they are not terminating, they are not ending, they are moving but they are not terminating, and they are not repeated. But for rational numbers you have something that is 0.333333. It is non-terminating but it is repeated. It will be irrational. But this one is irrational, whilst this one is rational. Thank you very much. This is the concept we had for today. So basically we've been talking about sets of numbers where you're supposed to be able to have an understanding of what numbers, kind of numbers we have: whole numbers, natural numbers, integers, rational, irrational, real, complex, and the like. So we dwelled much of our emphasis today on rational numbers. What a rational number is, a characteristic of the rational numbers, how to express those decimal numbers into fractions, and then also lastly we've talked about the definition of an irrational number, on how we can differentiate it to rationals. Thank you very much. Find time to pass through the document which we sent you, and yeah, you'll be able to learn more. So next time we'll look at the set theory. You know, School of Business sets is much more in terms of the practical aspect. It is less to do with the theoretical part of numbers, but more of the practical aspect. So we'll draw much into details in terms of the set theory in our next lesson, but go through the document which was sent on sets. Yeah, we'll meet next time. Thank you very much and enjoy your stay, even as we'll meet physically in next month. I believe you'll be reporting in November 25th, so we'll meet physically next month. Thank you very much and have a blessed day.